Okay. So, um, so last time we were looking at, or in the second half of class, was non-homogeneous equations that separate disturbed lineal problems. And last time I covered the general idea, but didn't have a chance for an example. So today, it's going to be all examples. But because examples are so involved, I'm only going to have time for 2 of them. But what I'm hoping is that this will be of substantial help for
Homework.
Yes, for homework.
Yay.
Okay. So. So finish chapter 6 this week, and then last couple of weeks we'll have for chapter 7. Okay. So a quick recap. So problem we're solving is r of x, m of t, du dt, minus p of x, ux, x, plus, whoops, okay, q of x, u equals big F of x of t on the interval AB. And then we have the boundary conditions equals b of u equals 0. So this is for a regular problem. And oh, that's right, there was a typo in our notes that I didn't fix last time. Okay. And then the initial condition. Okay. And what ended up happening is our solution as this form an of t, vn of x, where vn of x are the eigenfunctions of a Sturm-Liouville problem. Okay. Where this is our Sturm-Liouville operator, L of u in this case. All right. And then these coefficients are a solution of these non-homogeneous ODEs, m of t and prime of t plus lambda n a n of t, where lambda n are the eigenvalues of our regular Sturm-Liouville problem, is equal to Fn of t with initial condition n of 0 equals Fn, where our initial data has an eigenfunction expansion of this form, so the little fn are the coefficients of little f, and then big F of xt over the weight function r of x also has an eigenfunction expansion. So these expansion coefficients give us the particulars, like the initial data and the source term for our ODE. And we solve these ODEs for all n, and then we get the coefficients of our solution, our a n of t. And if this is a parabolic problem, if we had a hyperbolic problem of utt, the only thing that would change is that we have an double prime in the ODE, and then we'd have two initial conditions that come from the initial data, the two initial conditions of your PDE. And this ODE is then solved for each n using, it's linear, so you can solve by integrating factor. Yes?
Does that say an of 0 equals f of n?
Yes.
Right?
Yeah, that's
Okay.
0. Okay. All right. And in the notes, I have the solution formula for this equation obtained using an integrating factor. Because your integrating factor, which I'll call mu of t, is e to the integral of lambda n over n of s ds. Okay. All right, so now I'm going to go ahead and. Was there a question? Okay. I actually have. Okay, so two examples we're going to look at. One is actually going to be a wave equation, so we'll have UTT, so we'll have a second order ODE here. And then I have another example that's actually straight from the exercises. No, I did not assign it, but it's similar to ones that I did assign. So you can see how to work those out. Okay, now, let's see. Okay, all right, so we'll do this hyperbolic one first. Okay. All right, so we have UTT minus UXX. So this is our Sturm-Liouville operator L of U. So it's just basically minus second derivative. And our big FXT is a product of a function of x and a function of t. And we're working on the interval 0 to 1. And we're going to have Dirichlet boundary conditions. And then we have our initial conditions are both 0. So that's going to help matters considerably when we solve these second order ODEs. Okay, but we're still going to have some to solve because of this.
Is that a sine W?
Omega.
Oh.
Yeah, so this is a frequency problem. Okay, and I'm going to assume that m from here is a natural number. And I'm going to assume that omega is not equal to n pi in, m pi in absolute value. Oh, so not equal to. Actually, I'm going to consider both cases. First not equal to, and then we'll look at the case where we are equal. Okay. When we perform separation of variables, and we get our Sturm-Liouville problem, this is going to be v double prime plus lambda v is 0. And then we have Dirichlet boundary conditions. And we've seen this problem before, of course. So our eigenfunctions are sine n pi x.
Over 1, so.
What?
It's n pi x over L, but L is 1. Right?
Yeah.
So,
Okay. And then we have our eigenvalues. They're just the constant squared. Okay. Okay. So now But I represent the solution in this form, slight change in notation. So capital Tn of t are our coefficients that we're after. And this is our eigenfunction expansion of a solution. And to obtain these, we use the ODEs from previous board, except because we have a UTT, we're going to have a Tn double prime plus eigenvalue times Tn is equal to the following. Now, we take this and expand it in our basis of eigenfunctions also. But here we have assigned m pi x, which is one of our eigenfunctions. So if I take, so this is my big F of xt, and if I take big F of xt over r of x, which is assigned m pi x sine omega t over 1, our wave function is 1, and I expand that in my basis of eigenfunctions, well, all these coefficients, these big Fn of t, are going to be 0, except for a case where m equals n. So this right-hand side is going to be 0 when m is not equal to n. And when it is equal to n, because this is sine n pi x, so when n and m are equal, we're just going to get what's left, sine omega t. So, something to keep in mind in various homework problems, if you're trying to take an eigenfunction expansion of something that already is, the way it's written, a linear combination of the eigenfunctions you're expanding in, that's the easy case, because you can just pick off the coefficients. You can just read them off your formula. So that's exactly what happened in this case. And our initial conditions come from these initial conditions. They're both 0. So Tn of 0 is 0. Tn prime of 0 is 0. So in most cases, we have a completely homogeneous ODE that has a 0 right-hand side and also 0 initial data. So in those cases, the solution is going to be 0. So we could tell right off the bat that Tn of t is equal to 0 for m not equal to n. Because if there's no source term, there's no initial data, you're not going to have anything in your solution. Any questions so far before we get to the interesting part? So now still the case where m equals n. Let's see what happens. Yeah.
How do you know the wave function is 1?
Oh, because the coefficient of your time derivative is r of x, m of t. So r and m of t are both 1. Okay.
What's exactly how you test the sine omega t?
Oh, so really what you're doing is you're matching this up against this.
So we're just looking at the f values, not the whole summation.
Well, okay. Okay. So we had an interruption in the taping, but I think nothing was lost. Okay, actually, just in case, for those of you watching at home, I'm going to let you see the board a little while longer. Okay, pause as needed. Okay, now we can keep going. All right, so now from a case where n equals n. So our ODE is this. Tm double prime of t plus m pi, short, right? Tm double prime plus m pi squared tm is equal to sine omega t. And we're keeping in mind that absolute value of omega is not equal to m pi. Okay, now
Not equal.
It's
Ah.
not, yeah. It's,
not equal to. That kind of a day. What is Monday? Now, when you have a second order ODE like this that is non-homogeneous, what are the methods taught for solving this, like in 285, your first DE class?
Undetermined coefficient.
That's one. What's the other one? It is often taught right after undetermined coefficients. No? Variation of parameters.
Oh, I was gonna say that.
Well, why didn't you?
Because I guessed that as an answer last week and it was wrong.
Oh, okay. Whatever to you? You always answer these things.
I know. It's that kind of.
Okay, well, I guess if I can use that, so can you. Okay, but that's good if someone else chimes in.
Dang.
Okay,
Oh, I would have been right.
all right. So,
Well, at least I say stuff.
yeah.
I said stuff too! What?
Okay. No more escalation. Now,
I'm about to beat him.
okay, well, you can do that after class. Okay, you have to make sure I don't accidentally stop taping. All right, I like have the like variation parameters better, and it's actually more general, so that's the one we're going to use. So, a particular solution. Well, first, a homogeneous solution. Most of you don't remember variation parameters. Of Tm double prime plus m pi squared Tm equals 0 is there's two independent solutions. So we have cosine m pi t and sine m pi t. Now, if you take any linear combination of these, in other words, you multiply them by constant coefficients, that again will be a solution of a homogeneous equation. So we want a solution of a non-homogeneous equation, and the idea behind variation of parameters is
change variables, right?
no. Well,
I thought you like reduced it to a single order or something.
no.
Using different variables.
Oh, that's reduction of order.
Oh.
Where if you
Yeah,
only
there was
have
another
one of these, you use reduction of order to get the other one. Okay, well, it's good you remember stuff. So variation of parameters, our particular solution has this form. And actually, this is quite convenient in this case because our homogeneous solution is going to be 0 because the initial data is all 0. So the idea is instead of combining these with constants, we combine them using functions of t. So that's how variation of parameters works. If we just figure out what you want cosine m pi t plus u2 of t sine m pi t. And we just have to figure out what u1 of t and u2 of t are. But fortunately, variation of parameters gives us formulas for U1 and U2. And in this case, variance of parameters is useful for higher order ODEs in general, but for second order, at least we have a concise formula for these. So U1 of t is minus the integral from 0 to t of our source term sine omega tau, because I'm going to integrate with respect to tau. And then our second solution, sine of m pi tau, over m pi. M pi happens to be the Wronskian of our two solutions, cosine of m pi t and sine of m pi t. Okay. So it's a Wronskian that goes in a denominator. So at least in this case it was d tau. At least in this case it was nice and it was a constant. Okay. Now, this is a pain to integrate. How do we even start? Like, we can't integrate that the way it's written.
Orthogonality. No.
No.
Which, like the identity?
Sorry?
The identity, the trig identity.
Which? Okay. Yeah.
It's
Which?
like the,
Sine A, sine B.
one half sine of something minus something. Like,
Yes. Product of sum
Yeah. product
formula.
of something.
Yeah. So what you get is the m pi you can pull out, and so we're going to get a 1/2 also. So minus 1 over 2 m pi, and then we'll rewrite this product of sines is actually a difference of cosines. So you get cosine this minus this minus cosine of this plus this. Make it tau plus m pi tau d tau. Okay. Now we can integrate that. So we get, okay, so minus 1 over 2 m pi. Okay. And things get even messier still. So sine w minus m pi tau over omega minus m pi. So now we can see why we need omega to be not equal to m pi here, because we'd be dividing by 0. And then we have minus sine omega plus m pi tau over omega plus m pi. So now we see why we need it to be not equal in absolute value. Okay, so either plus or minus failed, we'd be dividing by 0. With limits 0 and t. Okay. Now, this can be condensed by putting everything over a common denominator. And if we have omega minus m pi and omega plus m pi, then we get a difference of squares as a result. So I'm going to, now fortunately if we plug in the limits, plug in 0 we get nothing, and so we'll plug in t for tau, so the tau just changes into a t. So after we plug in the limits and then we put everything over a common denominator, we get this mess. We get sine omega minus m pi t times omega plus m pi minus sine omega plus m pi t times omega minus m pi all over omega squared minus m squared pi squared. Okay, so that's quite rough. Now, so that is our coefficient u1 that goes right in here, and will get multiplied by cosine of m pi t. So questions about the process at least? Okay. Now, that's u1. we do a similar thing for U2, and due to time I will, the process is exactly the same. You're going to have to use a different product of some identity to carry out the integration. Okay.
So we just solved for U1, right?
Yeah, only U1. Now, U2, similar formula. So we have integral of our source term, sine omega tau, times our other homogeneous solution, cosine of m pi tau, L over Wronskian. Okay. Now, after carrying out the previous one, integration is exactly the same, so I'm not going to go through all that again. But here's the final result. Minus 1 over 2m, oh, that's a pi, not a tau. And then we have similar thing, except it's cosine, and the signs of everything are reversed. Oh, so omega plus m pi t, omega minus m pi, plus, so all the signs are different, cosine omega minus m pi t omega plus m pi. And then, when you plug in the limits 0 and t, when you plug in 0 into cosine, of course, you get 1. So you're going to get another term here, minus 2 omega. And all of that is over omega squared minus m squared pi squared. Okay. All right. So, now, we can form our solution. So T m of t is u1 of t cosine m pi t plus u2 t sine m pi t. Right. Now, oh geez, still many pages to go. How much time do I have?
Is a lot of it, a lot of your pages just like writing all the stuff?
Yeah.
Is that a lot of it?
Yeah, just because these expressions are pretty long.
We can skip a lot of the writing it part.
Yeah, well,
We know what everything is.
because the thing is, the final solution, after I put everything to simplify as much as I can, it actually, there's a lot of stuff that cancels. So what happens is, and yeah, I think in the interest of time, because it's also, is it true that those of you who are real analysis class starts at 4:45?
Yes.
Yes.
And
Okay.
goes on until 6:30
Through next week.
for the next 2 weeks,
So,
It's just 4 more days though.
yes.
which is 4
Um,
more than I want.
But then we're done.
Yeah.
But then we're done.
Um,
It's over.
so then what happens is, you take these cosines, and you expand them. So like this would be cosine omega t, cosine m pi t, plus sine omega t, sine m pi t.
Is that using another identity?
Yes,
Okay.
yeah.
Cosine A minus B, right? Cosine
Yes.
A minus cosine difference.
Yeah, so, and also expand this one too, and also the signs in the other formula. Expand everything. That's what you do. And this is done to a certain extent in the notes, where, because you can imagine, if I take this long expression and substitute it into here, and the other expression that's similarly monstrous, and plug it into here, I'm getting something super long, and then it gets even longer when I expand every single sine and cosine difference.
Then everything gets
Just about everything cancels because some terms are different signs. Also, you use sine squared plus cosine squared equal 1. So So you can imagine how, well, you can look in the notes to see just how nasty it is. It took 2 lines just to write it out. Actually, once I expanded it, it took 4 lines to write it out. But then, magically, everything condenses into 1 over omega squared minus m squared pi squared. And then you get omega over m pi. So in other words, this term survives. Sine m pi t minus sine omega t times sine of, oh, actually, that's the whole thing. So that's Tm of t. But then what you do is, this is your coefficient of sine m pi x in your solution, u of xt. So now your solution is all of this m pi t minus sine of omega t, and they get sine m pi x. Okay. Now, I want to point out for the homework, and yes,
Do you include the summation as well, or?
no need because this is the only term. Yeah. Normally you have,
Oh, because.
yeah, because
Then because when
Tn of t is 0 for n not equal to n. So yeah, you do have summation, but all your terms went away.
Yeah.
In the homework, when it presents you with a PDE to solve, and then it asks at the very end, is this a classical solution? For our purposes, yes, it is a classical solution if your initial data and your source term, your big F of xt, if they satisfy the boundary conditions, then it can be shown that yes, you do get a classical solution that satisfies the PDE initial boundary conditions at all relevant points. Now, our big F of xt in this case was sine omega t sine m pi x. That satisfies the boundary conditions. Your initial data was 0, so of course that satisfies the boundary conditions. So this is a classical solution. And that's because big F of xt and the initial data satisfy the boundary conditions. Suppose these items do not satisfy the boundary conditions. You can get things like Gibbs phenomenon, issues like that. You may get.
what would be an example like of a solution that would not be
Okay. For example, suppose my big F of xt was equal to sine omega t times cosine of m pi x.
not yeah.
Not classical, because that doesn't satisfy the boundary conditions.
Of course. Because that 0 is not going to be 0.
Yeah. That'd be a real pain to compute. Okay. Now, I want to comment on this solution and its behavior physically before I move to the case of omega equaling m pi in absolute value. Okay, so what happens here is u of xt is the displacement at the point x and the time t of a vibrating string. Well, in this case, because of the source term that's sine omega t sine m pi x, the displacement is operating at this fixed frequency, m. And what we have here is the amplitude. Okay. Now, notice that the amplitude does change over time. But look how it changes. Sine m pi t, sine omega t, where m and omega are fixed values. So it turns out that the amplitude is it what?
Like periodic as in like.
Yes, it's periodic. Well, this part has periodic period m. This part is periodic with period omega. But the point is, it is bounded.
Right.
Because any dependence on t, so I should say bounded, well, it's bounded in every sense, but it's bounded function of time, because the parts that depend on time oscillate between plus and minus 1. And we have these harmless factors here. So it's just going to keep, because the source term, big F of xt, is periodic in time, so it's going to keep supplying displacement to the string. In other words, it's like a string it's like a guitar string that's constantly being strung. You're always playing it. So it's going to keep vibrating, but in a bounded way, forever. So I want to contrast that with what happens if omega equals m pi in absolute value. So for that, okay, actually. So what happens here is, so now what I originally wrote here is correct, omega equals m pi in absolute value. We're still solving the same ODE, but then what happens is, okay, we still use variation of parameters. And I still have this same integral. But now I can take advantage of the fact that omega equals m pi in absolute value. So actually what I'm going to do for simplicity, I'm going to drop the absolute value, let omega equal m pi. And then the case of omega equaling minus m pi is similar. So since omega equals m pi, this becomes integral of, well, okay, minus 1 over m pi, integral of sine squared m pi tau d tau. So now I have to use a whole different approach. How do I integrate that?
Power reduction.
What?
Power reduction. It's like 1 minus cosine.
Yeah, half angle formula.
Half angle, yeah.
But yeah, that does reduce the power. Yeah, actually, I hadn't heard it by that name before, but it definitely describes what happens. Okay, so now I have minus 1 over 2 m pi, integral of 1 minus cosine 2 m pi t, m pi tau. Okay. So now I can go ahead and integrate all that and jump straight to the punchline. So this is minus 1 over 2 m pi t minus 1 over 2 m pi sine 2 m pi t. So now we have this factor of t that we didn't get in the previous solution. And then u2 of t is the integral of sine omega tau cosine m pi tau over m pi. M pi tau. And this becomes sine m pi tau cosine m pi tau 1 over m pi. How do you integrate that?
the double angle for sine.
You could. What's another way to integrate this?
Cosine
Oh,
2x.
no, you substitute.
U substitution, yeah. This is your U. And then your du is actually m pi cosine m pi tau, d tau. But then that m pi would cancel with this m pi. So actually, no. They'd be multiplied together. So basically, you get like u squared over 2 when you integrate times a constant. So what you get is 1 over 2m squared pi squared sine squared m pi t. Okay. So now what happens when you put everything together, following the variation parameters formula? So we have this function times cosine m pi t plus this function times sine m pi t. Actually, I want to keep my overall solution in the first case so that we can contrast it with the other case. So we're about to do. All right, so this is the omega not equal to m pi case. So omega equals m pi, what we get is Tm of t is u1 times cosine m pi t plus u2 sine squared m pi t times sine m pi t. Of course, that just becomes sine cubed. And what will happen in that case is now if you take this and expand it as a double angle formula, so you get 2 sine m pi t cosine m pi t. All right, so we have t cosine m pi t plus 1 over 2 over 4 m squared pi squared 2 sine m pi t cosine squared m pi t, because we get 1 from here and 1 from here. This 2 cancels, leaving a 2 down below. And then I have plus 1 over 2 m squared pi squared sine m pi t sine squared m pi t. So these two terms combine to give you, because you have cosine squared plus sine squared equal 1. So, so now my overall solution is what you're going to get from combining these two terms, and that's going to be 1 over 2m pi times 1 over m pi times what's left here, which is sine m pi t, minus this, t cosine m pi t. So this is Tm of t times your eigenfunction, which is sine m pi x. And that's it. So here's a solution when omega is not equal to m pi in absolute values. Here's where we are equal. What happens to the amplitude in this case as a function of t? It's unbounded because of this factor of t right here. Okay, so what happens is, this is an effect that's called resonance. Okay, so what's happening is the frequency that your source term is causing vibration in as a function of t matches the frequency that it has as a function of x. Because of the source term has this sine m pi x factor in it. But the way the frequency is varying over time coincides with that. This is something that is quite relevant when it comes to structures. Structures, buildings, bridges, and so forth, can actually collapse if they're vibrating at the wrong. If you get a vibration that should say the absolute wrong frequency or right frequency, depending how you look at it. So if it hits it just right, the vibrations just get out of control. And at some point, so what will happen in this case, physically, is vibrations in a string would grow and grow, and what happens to the string? At some point, it's going to snap. So that's why it's very important to understand both of these cases, that the solutions can behave very differently. Okay, so questions about what happened there? Okay, so that's that example, and now I have another example that's a parabolic problem that pulled from the exercises. Well, due to time, I might have to do this in a somewhat abbreviated fashion.
In this case, as t increases, it becomes like an increasingly big negative term.
Well, because of the oscillation that's multiplied by the cosine, it'll go
huge.
large positive and negative. It's going to be all over the place. Yeah, I guess it's always negative, then it means that the string keeps getting pulled and pulled and pulled. And it snaps. Either way, it snaps. Okay. So for this example, we have ut equals uxx minus u. So this also we see in certain problems. So this is a slightly different Sturm-Liouville operator. And then our source term plus 2t plus 15 cosine 2x. So this is our big F of x and t. And we're on the interval 0 to pi over 2. Our boundary conditions are Neumann, du dx at 0 to 0, and du dx at pi over 2, 0. Okay, our initial condition, 1 plus the sum, n equals 1 to 10 of 3n cosine 2x. Okay. So when you get separation of variables, these are the ODEs you get from separation of variables. You have t prime plus lambda t is 0, so that's the usual. And then your spatial ODE is x double prime plus lambda minus 1 capital X is 0. It's minus 1 because of the minus u term there.
Maybe 2 and x in your initial condition.
Yes. Oh, typo in the notes. Yes, it is supposed to be 2 and x. Okay. And these are bounded to x prime is 0 and x prime of pi over 2 is 0. And as a result, well, because the derivatives are 0 on the boundary, that means it's going to be cosine. So your general solution, okay, so actually, yeah, so my eigenfunctions are going to be cosine of 2nx, because normally it's going to be n pi x over L, but L is pi over 2. So, okay, so that's n pi x over pi over 2. So that's usual behavior. But our eigenvalues, so lambda n, because what we need is, to satisfy the boundary conditions, we need square root of lambda n minus 1 to be a multiple of of n pi over,
Wait, pretty much 2n pi.
yeah,
Or 2n.
yeah. So actually, all right. This comes about from satisfying the boundary conditions. So that means that lambda n is equal to, well, pi's are going to cancel. So I'm going to get 1 plus 4n squared. So those are the eigenvalues. And n equals 0, 1, 2, etc. Now, those of you who are not sure why this came about, keep in mind this general solution is a constant cosine of square root of lambda minus 1 x plus b sine square root of lambda minus 1 x. So it proceeds in the exact same way as other simpler problems where you have like x double prime plus lambda x equals 0. It's just whatever expression you have here goes under the square root sign there. And then you apply the boundary conditions in the same way as before. And that led to this condition, which led to this eigenvalue.
Can you explain why it's randomized molecules?
Because of a minus u. Yeah. So if you have a u term here with a constant coefficient, that causes a constant shift in your eigenvalue of equal to that coefficient. Yeah. So there's a couple homework problems where this that minus 9/4. Yeah.
9u for.
Yeah. So I figured I'd do a problem that had that. Okay, so now the solution has this form. U of xt is the sum of coefficients times cosine 2nx. So eigenfunction expansion. And the coefficients a and t satisfy these ODE. So a n prime plus lambda n a n is equal to big Fn, and a n of 0 is equal to little fn. So these are the eigenfunction expansions of your source term and your initial data. So what we have is big F of xt, which is 2t plus 15 cosine 2x, is an expansion of big Fn cosine 2nx. And similarly, our initial data, little f of x is 1 plus this sum of 3n cosine 2nx is an eigenfunction expansion of little fn cosine 2nx. So both of these, big F and little f, are already linear combinations of your eigenfunctions. So you can read off the coefficients. So from this, in this case, for example, big F0 is the coefficient that's of a term that's constant in x. So that's going to be 2t. And then when n is equal to 1, so big F1 of t is equal to 15. And all others are 0. Okay. What about little f? So we want little f0, little f1, and so forth. What can we get for those?
F0 is 1. Fn is 3n.
For which n?
For all.
Not all of them. Oh, this sum is not, that's not infinity.
Oh,
It goes up to 10.
well then up until 10.
Yeah. So from 1 to 10, whoops, that's not right. It is 3n, and then all others are 0. So most of the coefficients are 0, so that's nice. So now we can take a look at all the possibilities for these ODEs right here. So for instance, if you look at the n equals 0 case, we have a0 prime plus lambda 0 a0 is equal to big F0, which is 2t, and a0 of 0 is equal to 1. That's little f0. So that one has non-homogeneous source term and initial data. A1 prime plus plus lambda 1 A1 is equal to big F1, which is 15. And A1 of 0 is equal to little f1, which is 3. And then for n going from 2 to 10, so a n prime plus lambda n a n is equal to 0, because there are no more big F coefficients. And a n of 0 is equal to 3n. And this is n going from 2 up to 10. And then finally, an prime plus lambda n an is 0. A n of 0 equals 0 for n greater than 10. But what happens in that case? So for n greater than 10, the ODE is homogeneous. The initial data is 0. So what does that tell us? What can we say about an of t in that case? Yeah, it's going to be 0. Because it's a linear ODE. No initial data, no source term, the solution is always 0. So if your source term and initial data are linear combinations of a finite number of eigenfunctions, then you can have infinitely many of your coefficients of your solution equaling 0. It's just a matter of which ones. So we still have these cases for n going from 0 to 10. We still have something to solve for. Yeah.
I have a question. Over here on the right, you have a little f0 equals 1.
Yeah.
And then right next to it, little fn equals 3n.
Yeah.
But right under that, you have little fn is also equal to 0.
For n greater than 10.
Oh.
Yeah.
Oh, greater. That does say greater than. Okay.
Okay.
Never mind.
Good to know. All right, so now these remaining ODEs for n going from 0 to 10, we need to solve those. set of nums. So you'll have a slight break before analysis. But again, there's a good chance that Dr. Ding will be slightly late anyway.
Hopefully.
He's never late when we start early. He's never late when we start early, yeah.
Oh, well, there's been times where I needed to cut the class short, and then I saw that he still wasn't ready, so I was like, oh, okay.
No.
I stopped early for nothing.
He's
Okay.
never late when we start early.
Okay. Fine. So A0 of t is, well, you could use, okay. Well, lambda 0 is equal to 1. So you have A0 prime plus A0 is 2t. So your integrating factor, mu of t, is e to the t. So your solution is going to have e to the minus t plus integral from 0 to t e to the minus t minus s 2s, that's your source term. Now that would, how would you integrate that? What would you need to use? Integration by parts. I'll just fill out the final results since I'm almost out of time anyway. So we get 2t minus 2 plus 2e to the minus t. And yes, the first term and last term could be combined, but I want to show this comes from initial data, and this part plus comes from the source term.
How do you get lambda 0 equals 1?
Oh, because lambda n is 1 plus 4n squared.
Right. Okay.
Now for lambda 1 is equal to 5 for that reason.
Right.
So
The 5t.
yeah, a1 of t is the initial value, which is 3, times 1 over the integrating factor, e to the minus 5t, and we have integral from 0 to t, e to the minus 5t minus s, 15. So at least this integral is straightforward. So you have 3e to the minus 5t plus 15, e to the minus 5t minus s over minus, actually plus 5, with limits 0 and t. So it's plus 5 because we're integrating with respect to s. So when you plug in the limits and simplify as much as you can, you actually get 3e to the minus 5t, plus 3 minus 3 e to the minus 5t, and these cancel, so you're left with is 3. And then n going from 2 to 10, so lambda n is equal to, well, 1 plus 4n squared. So for n going from 2 to 10, that's a simpler case because you have your initial value, which is 3n, times e to the minus 1 plus 4n squared t. And you don't get an integral because there's no right-hand side.
Those are 0, right?
What?
Like, those are zeros? Something is 0, right?
Oh, this is from 2 to 10.
Yeah.
And for n greater than 10, they're all 0.
Oh, for n greater than 10.
Yeah. Yeah, but for this one, yeah, since the right-hand side is 0, that's why we only get this.
Okay.
Where did you
Right,
get
okay.
lambda 1 is 5?
What?
Where did you get lambda 1 is 5? You got the,
From this formula.
oh, okay.
Okay.
Oh, okay.
Right.
So now we could put the solution together. So it's A0 times V0, which is 1. And then we have a sum of a n of t cosine 2nx. So when we put that all together, we get a0, e to the minus t plus 2t minus 2 plus 2e to the minus t times 1 plus a1, which is 3, times v1, which is cosine 2x. And then we have a sum, n equals 2 to 10, of a n of t, so that's 3n e to the minus 4n squared plus 1t cosine 2nx. And since all other an of t are equal to 0, that's all the terms we have. So our summation stops at n equal 10. Okay, I had to rush that unfortunately because of time, but it's also all in the notes that this is how you're solving for these coefficients, whether it's a parabolic or hyperbolic problem. Well, especially for parabolic problems, it's first order ODE. So you're using your integrating factor method, or if there is no right-hand side, it's a straight separable equation. So it's easier to solve in that case. So you have, in other words, you have to dust off your knowledge of how to solve linear first order ODEs from Math 285, or whatever you took. Okay, but then you can solve these ODEs, and based on your initial data and your source term, you break down the cases differently for different values of n, depending on what your coefficients of those things are in your eigenfunction expansion. Because of what was 0 and non-zero for different values of n, that's what gave us all these ODEs, and we also saw which ones have nothing, where there is no coefficient. Okay. So that was non-homogeneous PDEs. On Wednesday, we'll look at non-homogeneous boundary conditions and how to make them homogeneous. Okay.